Hello, in this video I will do example 4 of optimization word problem. So example 4 optimization word problem. A dairy farmer plants to fence in a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing? So they want the least, not the largest amount of fencing if the fencing is not needed along the river. So first step is draw the best image you can think of. So let's use the Galaxy font. So let's say you had a river, right? It was right here. And you're gonna create fencing on this rectangular space, right? We don't need any fencing in the river, right? Uh, Hopefully the animals will not jump into the river. I think they're smart enough for that. So we got to find the fencing that'll give us the least amount of fencing. So let's call this side, let's call it a base. You could call it A, you could call it X, you could call it whatever. I'll just call it B for base. And then let's call this length here height. Okay, so what do we know? We know that, okay, so we found we draw the best image we can. Then we have to come up with two equations. So they tell us that the pasture must contain 100 square pasture must contain 180,000 square meters in order to provide enough grass. So that's like the area. So the area of this would be base times height, and it has to be greater than 180,000. So I guess you could say 180,000. And then our second equation will be like the perimeter. So we know that the perimeter is adding up both sides, but keep in mind we don't need this length here by the river. So our perimeter would be, so we only have two bases, so that's 2b and one height. So that's the second step. We found our two equations. Then what you're going to do next is you're going to substitute one into the other. So what should we do? Let's use this equation and then let's solve for b. Yeah, because that'll give us, and then we'll plug it into this equation. So that'll give us everything in terms of h, right? So let's use this equation. Let's solve for b by dividing everything by h. So it's going to be b equals to 180, 234 all over h. Okay. Then we just substitute in our b value into this one right here. So that would be p equals 2 times b, which is 1, 2, 3, 4, 4 over h plus h. So that would be 2 times 18,000 would be like 36,000. 1, 2, 3, 4, 2, 3, 4 over h plus h. Okay. What to do next is okay, so I'm going to take the derivative of p, set it to 0. But first, before I do that, maybe I can rewrite this part right here as 36 h to the -1, right? I think that would be a lot easier when we take the derivative. So we could just take the power rule. So let's take the derivative implicitly in respect to h, and then set it to 0. So on the left side, what's the derivative of p in respect to h? It would be dp dh. This side, what's the derivative of this in respect to h? It would be power rule. So -1 times that is -36,000. And then it's going to be h, and then whole power -1, so that would be -2. And you don't have to put dh over dh because that just becomes 1. The same thing here, what's the derivative of h? It's just 1. And like I said, you don't have to put the dh over dh. Okay. Now what I'm going to do is set this to 0, set your derivative to 0. Maybe I can rewrite this as a positive power, so I can rewrite this as -36 for h squared plus 1. Okay. Now go ahead and continue solving for h. So what I would do is subtract 1 from both sides. You get -1 equals the -36. 1, 2, 3, 4. All over h squared. Cross multiply, so h squared times -1 is -h squared. And then 1 times -36,000 is -36. Get rid of this -1 by dividing both sides by itself. So you get h squared equals to 36. 1, 2, 34. And then when you take the square root, you get exactly plus or minus 600. I think we are in, what are we in? Meters. 600 meters. But, you know, it just wouldn't make sense to use a minus because you can't have a height that's negative, right? So I think we'll just use the positive 600 meters. Okay, so hopefully this height will give you a minimum, right? Because we want a least amount. So we got to verify it. We got to check if this actually does give us a minimum by doing the test point method. So put 600 on number line, test region 1, region 2. We're going to plug in it back into your first derivative, which is, what is our first derivative? This one right here. Oops, dpdh. Okay, let's test region 1. I need a number less than 600. Maybe I could do 0. This would be, no, I can't use 0 because this will make it undefined. What if I used, let's just use 1. So this would be -36. 1, 2, 3, 4 plus 1. -36,000 plus 1 is definitely still a negative, right? I don't really care about the numbers, just a sign, so it's a minus. Let's test region 2. I need a number greater than 600, maybe 605. So when you put it all in the calculator, you do get a positive value. So you're going to put a plus here. So according to curve sketching, if you have a minus and a plus, you'll have what's called a local min. Okay, so this proves that 6h, our 600 meters will give us a minimum value. Okay, but what were they asking? They're asking what dimensions require. So we got to find our dimensions. So we found our heights. Let's find our base. So how do you find your b? B is right here. B equals 18,000 over h. So it would be 18,000. 1, 2, 3, 4, 1, 2, 3, 4 over height, which is 600, which is 300. Okay, so our dimensions will be 300 meters by 600 meters. Okay, so that would be our dimension. Okay, so that wraps it up for this optimization problem. This is example 4.